Today we will see in detail the harmonic perturbation, emission and absorption process, and also the photoelectric effect. According to the first order time dependent perturbation, CK1, uh, that is probability amplitude C sub k, is defined as 1 over IH cross H prime sub Km. We have already seen this, and integrating over 0 to tau e power I omega Km tt. We are integrating with respect to time. So now for harmonic perturbation, let us say we are perturbing the system by applying the harmonic function that is sinusoidal in nature. That is sin omega t with multiplication factor 2. There is a mathematical reason for why we are introducing this 2. After all, this is the multiplicative factor, it will not affect your result. By definition, this sin omega t can be written as e power I omega t minus e power minus I omega t divided by 2i. Now you can understand this 2 and 2 will get cancelled. Uh, and I will become I square minus 1. So minus 1, of course you are multiplying this with I e power I omega km t. So now if you multiply this I and I, you will get I square, which is minus 1 1 over h cross h prime sub km, and we are separating this into two integral. One is with plus sign, that is e power I omega t plus omega km. So this is what I have written, omega km, this omega km. Here you have plus omega, so plus omega tt, and minus e power same omega sub km minus omega t tt. So we have separated this integral into two parts. Now we got this expression. If you integrate the first term, you will get e power I omega km plus I omega km plus omega t divided by omega km plus omega. If you apply the limit 0 to tau, then if you apply upper limit, this t will become tau, and lower limit it will be 1. So this exponential term minus 1 divided by omega km plus omega. And also this for second one, here instead of plus you are getting minus. So applying limit, you are getting the same thing. From this structure we can understand one important parameter. uh, Out of these two terms, any one of the term will get dominated. Say for example, here I have mentioned if omega km is equal to minus omega, this one, then this will become 0. So this will be infinite. So first term will dominate, second one you can ignore. So let us take the case where omega km is equal to minus omega. So the probability of particle moving from mth state to kth state is, you just take the modular square of this probability amplitude. Then you will get, if you take modulus square of 1 over IH cross, you will get 1 over H cross squared, and this is modulus H prime Km whole square, and this will be because we are taking only the first term, exponential Km plus omega tau minus 1 divided by Km omega km plus omega whole square, because we are squaring it. Now we will try to simplify this. We have seen that the transition probability is 1 over h cross squared modulus h prime sub km square, and modulus, this is also modulus, remember that, e power I omega km plus omega tau minus 1 divided by omega km plus omega modulus square. Now you take the numerator. So if you take the numerator, let us say this is e power minus I, sorry, plus, here it is plus, e power plus I theta minus 1 square is equal to 4 times sine square theta by 2. This we have seen in detail in our previous lecture on constant perturbation. So I am replacing the numerator by 4 sine squared omega km plus omega tau divided by 2, and this I brought here omega km plus omega square. Now this is I am rearranging the term. So I am taking sine squared omega in the numerator, omega km plus omega tau divided by 2, and in the denominator I am taking this, I am bringing this 4 into the denominator. So this 2 squared will become 4. So I brought that 4 here, and I have multiplied and I am multiplying and dividing by pi tau. Here also pi tau, here also pi tau. Now the parameter which I have shown in red color box is nothing but the delta function. This is equal to delta omega km plus omega divided by 2. So this is the delta function. Of course you have this pi tau, because you are dividing this by pi tau in order to make this as delta function. So you got this delta function. Now you know very well that omega km, what is omega km? That is angular frequency, which is equal to E k minus E m over h cross. This also we have seen already. So you replace this, that is now you bring this h cross omega here. So h cross omega km is equal to ek minus em. So this will be h cross, here h cross. So you are multiplying and dividing by h cross. From delta function property, delta Ax is equal to 1 over modulus A delta x. So this will come into the numerator. So I am taking into the numerator. So 2 h cross delta Ek minus Em plus h cross omega pi tau. Now we will rearrange the term now. So we have seen that the transition probability is this one. Now we are going to remove some of the terms. Say here this h cross will get cancelled with this h cross square. Then you bring this tau, the transition rate is defined as the transition probability per unit time. That is, you have to bring this tau to the left hand side. So I have brought it. That is transition probability divided by this tau is equal to transition rate. Here in the numerator you have 2 pi, this pi also, 2 pi divided by this h cross and modulus h prime sub km, modulus square actually, then this delta function. Here this function will have non-zero value, only this is 0. That is Ek minus Em plus h cross omega is 0. That means Ek is equal to, if you bring this 2 to the right hand side, then this will become Em minus h cross omega. That is, the final energy is smaller than the initial energy. That means it is a emission process. It's called stimulated emission, because it releases the energy by an amount of h cross omega. So this is called stimulated emission. Similarly, if second term of the following expression is dominant, that is, just now we have seen this is first term is dominant. If second term is dominant, what will happen? This will be dominant when omega km is equal to omega. So when it close to 0, this will be the dominant one. So then the rate of transition will be gamma m to k is equal to 2 pi h cross h prime sub km modulus square delta ek minus em. Here instead of plus h cross km, in this case it is minus h cross km. So, because we are following the similar one we have followed for stimulated emission. So, this transition is non-zero only if this is 0. The argument of the delta function is 0. That is Ek minus Em minus h cross omega is equal to 0. If you bring this to the left hand side, these two terms, last two terms, then you will get Ek is equal to this one. Ek is equal to Em plus h cross omega. This means final energy is higher than the initial energy. So, this process is called absorption, because your final energy is less than this initial energy. That means it absorbs some energy, that is, it absorbs energy by an amount of plus h cross omega. So this is the absorption process. Then we will move on further. If we draw the graph between sine squared omega km plus or minus omega tau over 2 divided by omega km plus or minus omega k squared, which we have done in the case of constant perturbation, and we have dealt in detail that the peak is at tau squared over 4. So in that case, we in earlier case, that is constant perturbation, we have taken x-axis as tau. Here we are taking x-axis as plus or minus omega km. So that is the difference. Another difference is that peak appeared at 0, tau equal to 0. Here peak appears at omega. That is omega plus or minus omega km is omega. So, height and width of the main peak is centered around omega. Earlier case it is centered around 0. So, same explanation. Decays rapidly when omega km moves away from omega. And height is proportional to tau square, and width is proportional to 1 over tau. Hence, the area under the curve is proportional to tau. Since most of the area is centered around this point, so you will get transition probability here, maximum transition probability at this center. Now we will move further up. So far, we have seen the emission and absorption process. Remember that in the case of constant perturbation, it will not release energy or absorb energy. So the transition is between the same energy state. In the case of harmonic perturbation, it releases or it absorbs the energy. That is a major difference between the constant perturbation and harmonic perturbation. The photoelectric effect, now we will move on to photoelectric effect. We have seen the transition probability is equal to this one, 4 modulus h prime km squared divided by h cross squared omega km plus omega whole squared sin squared omega km plus omega tau divided by 2. The total transition rate associated with the transition from initial state um into the continuum final state uk, that is transition between uk we have to find now. Let us say the rho of ek is the density of final state final state. Here I have already explained this is initial state m and final state k. So the density of state is rho of k, that is number of state per unit energy interval, that is the number of final state within the energy interval t minus ek, ek minus TEK and EK plus TEK. Then the total transition rate gamma m to k is that is gamma m to k is we have to integrate, because for the entire density of this is for an interval TEK. So we have to see the probability for the entire system. So that means you have to integrate rho of EK TEK with respect to TEK. Now I will explain this process using this simple diagram. Let us say EI is the initial energy and EF is the final energy. There is a transition from this level to this. So we are going to find the transition between EK. Of course, this is EK. We are going to find the transition between EK minus TEK. This is lower, this one, to upper. Upper is EK plus TEK. So now we got this relation. Rate of transition is gamma m to k is equal to this one. Transition probability divided by tau and this one. Now I am taking 1 over tau outside. Now I have to integrate between this and this in order to find the rate of transition. So then rate of transition is equal to, I am taking 1 over tau outside, and the limit is ek minus tek to ek plus tek, and this transition probability is 4 times h prime km modulus squared divided by h cross squared, which we have seen already, and sin squared omega km plus omega tau by 2 divided by omega km plus omega whole square. Now I want to bring this denominator to the argument of this omega km plus omega tau by 2. That is x is equal to omega km plus omega tau. Then x squared is sin squared omega km plus omega tau divided by 2. I am taking this argument as x. This is x. I like to bring this also in the form of x. So for that here you have one extra term tau by 2. So we have to multiply and divide by tau by 2. We have to multiply this by tau squared. That means in the denominator. Then you have to add this into numerator also. Tau squared by 4. So that now we will get like this expression. This is the x, value of x. So naturally this denominator is x square. Now we have to change this tk, tek. Now we have taken x as omega km plus omega tau divided by 2. Then if you differentiate this x with respect to omega, then you will get tx is equal to tau divided by 2 t omega. Then t omega is 2 times 2 divided by tau into tx. So now you know t omega, we have seen t omega is equal to 2 divided by tau tx. Then I am going to multiply both sides by h cross. So t omega t h cross omega is equal to h cross 2 pi tau tx. This is nothing but tek, this one. I have shown this te1, tek. This is ek. So naturally I am replacing ek by h cross this one. H cross 2 divided by tau tx. If when tek is very small, then we can change the limit from ek minus tek to ek plus tek as minus infinite to plus infinite. Now I am rewriting this. Before that we can cancel some of the term. I can cancel this 4 and this 4. I can cancel this tau with this tau square. So outside the integral I will get only tau. Then remaining term is modulus h prime km square divided by h cross square. This is sine squared x divided by x square. And rho of ek, here you have one h cross because I have replaced tek by this one. So h cross 2 tau tx. So now you can see this h cross will get cancelled with this h cross square. Similarly, this tau also will get cancelled with this tau. Then you will get only 2 you can bring outside. So this is between the limit minus infinite to plus infinite. So we have seen the transition rate from m to k state is 2 times the integral minus infinite to plus infinite modulus square of the h prime km over h cross sine squared x divided by x squared rho ek tx, rho of ek tx. Now you can take all the constant outside except this x with the terms contain x. So this will become integral between minus infinite to plus infinite sine squared x divided by x. This is the standard integral. The value of this integral is pi. So I have taken this as pi, 2 pi over h cross, the modulus h prime km squared rho of ek. So this transition rate depends on the final density of state. Thank you very much for watching my video and supporting me continuously. Thank you very much.